Hello, everyone. Welcome to Keep Your Hadoop Cluster at Its Best. My name is Chris Naroth, and if we could advance the slide there. My name is Chris Naroth. I'm a principal engineer at Hortonworks. I work primarily on Hdfs, and previous to that, I had experience running and operating Hadoop clusters, so I come from a bit of an operations background. Sheetal found this picture of me on the internet. It's a very old picture. I don't look like that anymore. I look very young there, and I have kind of a smile on my face. That photo was taken before I worked on Hadoop operations.
And my name is Sheetal Doris. Hello. Hello. Okay, I'll try to talk a little louder. I'm engineering lead for SmartSense at Hortonworks. And same here, the picture that you see here is a picture of me before I started using Hadoop. You can see me smiling here. So personally, most of my career I have spent with customers in the field solving real-life business problems. Specifically, last more than 6 years, I have been working in Hadoop ecosystem, which includes Hadoop and all its ecosystem components, as well as other components like Storm, Kafka, Elasticsearch, Solar, et cetera, et cetera. So over the next few minutes, what we're going to do is we're going to talk about days in the life of Hadoop users. Both me and Chris have seen Hadoop very, very closely. We have seen Hadoop from different angles. We have been users of Hadoop. We have been developers of Hadoop. We have worked with multiple customers, hundreds of customers who are using Hadoop and seen actual problems, real-life cases, fire drills, as well as wars that are performing on the field. Both me and Chris have many war scars on us of all the Hadoop operations. What we really want to do is talk to you guys and walk you through those stories and make sure that you don't get into those pitfalls that we have already seen, so that your Hadoop operations journey can be much more smoother and fruitful. So through the stories, we'll again talk about what are the key challenges of Hadoop operations. And finally, we'll talk about how to win such wars, or preferably, how to avoid such wars. And finally, we'll have questions and answers.
All right, diving into the war stories that'll motivate this entire discussion. The first story that we'd like to discuss is a problem with the name node. This was experienced by the symptoms reported by the user were that the name node was periodically becoming unresponsive. This was an HA deployment. So what would happen is that it would fail over to the standby name node. That part is all by design. Hdfs HA is supposed to take over at that point and fail over. The problem was, in this case, it would fail over again after a very short time. And over a period of time, we observed flapping. It would fail over back and forth in between the two paired HA name nodes. And overall, this would have a negative impact on cluster uptime. The root cause for this problem turned out to be garbage collection. The name node is the central point of storage of metadata in an Hdfs instance. And as the heap grows to accommodate growing metadata sizes, there tends to be more requirements to tune garbage collection correctly. The impacts of misconfigured garbage collection start to be seen in a greater way. And in this case, that turned out to be the root cause for this problem.
The next story is about a customer who has seen extremely high CPU utilizations. Specifically, the system CPU was very, very high, and corresponding throughput was extremely low. What they have seen is that jobs are performing slower, and they're seeing extremely high CPU and much lower network throughput. When we actually digged into this and we figured it out, the actual problem was that they had THP, transparent huge pages, turned on. So THP is a feature in Linux to be able to help you transparently exchange large pages, extremely large pages. But unfortunately, certain versions of Linux, specifically Red Hat 6.5 and below, have serious performance implications of THP enabled. So you can see that in this particular graph, the red part is the system CPU. You can see it's extremely high. It's not normal for any system. The system CPU should not be such high. In fact, the user CPU is much lower. It should be other way around. And you can see on the other graph, the line graph, you can see that network throughput is extremely low.
Next, coming back to Hdfs once again, this was an incident of a cascading failure in Hdfs. The symptoms that were reported, the sequence of events that were reported by the user were, we performed an Hdfs upgrade. This used the Hdfs rolling upgrade feature. After that upgrade, Hdfs utilization kept on increasing. And in response to that, the user tried to delete a large amount of data, but despite deleting that data, space was not freed up. At that point, the operator thought that this might be a problem of cluster imbalance and decided to run the balancer utility to try to restore balance, an even distribution of blocks across the nodes in the cluster. But in fact, that did not address the problem, and it actually, in some ways, made things worse by increasing overall load on the system. And eventually, Hdfs became unresponsive. The root cause in this case turned out to be failure to finalize the Hdfs rolling upgrade. When an Hdfs rolling upgrade begins, the name node enters into a special state where it will not trigger block deletions. It will not trigger physical block deletions at the data nodes. And the reason for this is to support the possibility of a rollback of the upgrade, a return to the prior version of the software if the operator deems that the upgrade is not successful in some way. To support that requirement, physical block deletions are not occurring during this window, and that's so that we can restore those blocks later if needed. If the upgrade is not finalized for a very, very long time, though, which is a separate administrative step, then eventually a cluster can run out of space.
So you can see that one simple such step can make serious impact on your clusters. So small things definitely matter in longer run. The next story is of a customer who came back to us saying that their cluster is overloaded. They have many, many jobs that are running in their cluster, but most of their jobs are waiting for container allocations. And they see that all their yarn capacity queues are always fully loaded. It means that their cluster is overloaded, and they're not able to execute jobs that they wanted to execute in a day. In fact, they had some jobs that were waiting for literally 15 hours to get a container. When we digged into this and when we analyzed it further, what we actually found out is completely opposite story. Their cluster was completely underutilized. So when they did POCs, in their initial POCs, they chose a couple of jobs which needed large containers, 8 gigs containers. And after POCs, they decided to carry that same configurations into production. But in reality, most of their jobs never needed large containers. So you can see in the graph where the red part shows that the amount of memory that was blocked but unused by each container and each job in their cluster. So every job was asking for 8 gigs of container. In reality, they were just using 2 gigs. It means that many, many jobs were just holding resources, not using them, reducing your overall cluster throughput. So it was all because of suboptimally configured container sizes.
Once again, coming back to Hdfs, something we see surprisingly often is accidental deletion of data. And in a very extreme case, this might be a user accidentally running Hdfs dfs-rm-r recursive right on the root directory. Hdfs is great at dispatching work in parallel, including deletes across the whole cluster. If you Control-C to try to abort out of this command, that does not, unfortunately, have the effect of canceling the deletion that you just issued. This is because the command is issuing a remote procedure call to the name node, and Control-Cing the console application does not really cancel that RPC as it's executing in the background. The user responded to this by trying to shut down Hdfs immediately once they realized what was going on. Once Hdfs was down, there was a theory presented that if Hdfs trash was enabled, then that data was not really deleted. It would have been moved to a special trash area, and then it would have been able to be restored. So Hdfs was restarted, at which point it resumed all the block deletions because trash was not, in fact, enabled in this cluster. Once this happens, it's very, very difficult, nearly impossible to try to recover from that by doing things like OS-level undeletes of the blocks. This is distributed across all the nodes in the cluster. Even if you do manage to undelete those raw blocks, how do you figure out how to glue things back together into logical files as they existed previously in the name node? It's a very hard problem, and unfortunately, this is something that we see very often. And it has even happened multiple times for the same cluster, different users accidentally issuing deletions that they should not have.
And the last story that we have is about a user running high query. All they just wanted to know is, what is the running total of my total sales for today? Extremely simple high query. When they initially developed this query and tested it, all worked fine. But when it goes into production, they realize that this query is mostly returning right results, but sometimes it just starts giving random results. Every time you execute a query, you get a different result. Not because data is changing. Data is absolutely not changing. There is no new data coming in. There is no data being deleted. But every time you execute a job, different results. So obvious question was, okay, let's look at query. Is anything wrong in the query? Nothing seems to be wrong. It's extremely simple query. Just sum the amount from sales table where date is equal to today's date. The functions basically are Hive functions that find out what is today's date. Nothing wrong in Hive query. Next thing is there anything wrong in the data itself? Analyze all data. Nothing wrong in the data. Is there anything wrong in the Hive? Is the Hive having some bug that is manifesting into this problem? All analysis done, nothing found out. Later we figured out that there is a peculiar pattern that when you run this query during office hour, it always returns correct results. But when you execute on after office hours, it returns wrong results every time. So maybe actually just like nobody likes to work after office hours, maybe computers also don't want to work after office hours. But the actual problem when we digged into this was very different. One of the hosts in that entire cluster had different time zone. What it means is that based on which task goes on that particular host, or how many tasks get executed on that host will evaluate today's date as different date, which might be totally different than all other hosts. So such simple things actually result into different manifested problems, which are extremely hard to debug. It seems so obvious that this is easy to figure out and fix it, but how can actually relate these different problems, Hive query returning random results, to actual OS issue, an OS configuration issue? Very, very hard. And these kind of stories just keep happening more and more and more. There is absolutely no end to these kind of stories.
We can definitely see from these stories that there are some operational challenges associated with running Hadoop. Is there any way we can look at patterns that are happening in the field, look for common errors, and hopefully do something about them to try to prevent them? When we look for causes of some of these issues, something that really sticks out for me is that Hadoop simply has a lot of configuration knobs. At one point, I did a scan of what are all the configuration properties, even just at the core layer of Hadoop. So the core being Hdfs, Yarn, MapReduce. I came up with a count well over 300 possible configuration properties. And the nature of my scan just covered documented configuration properties. There are also some undocumented configuration properties in the code that might be in use. And again, that's just the core. If you broaden your search, look to other ecosystem components like Hive and HBase, it's even more. Then you might even have to consider different configuration properties for the core in combination with the components, so it becomes a very complex problem. And unfortunately, another complicating factor is that the best practices for these configuration properties are evolving all the time. One driver for evolving best practices is changes in hardware. As hardware changes, tunings that made sense for the previous generation of hardware might not make sense anymore. Another source of change is simply the software versions. We're constantly seeking to improve the software, so optimizations performed in a subsequent version might turn out to invalidate prior good configuration. Another problem is that there is no cookie-cutter, copy-paste, one good solution for configuration that applies equally across all the clusters in the world for all the possible workloads. It turns out to be cluster-specific and workload-specific. So an optimally configured cluster, in one case, it's not necessarily the case that copying the files will work just as well in another cluster. And also, optimally configured clusters may turn out to be unoptimal over time as things change. Things need tuning over time. All of these problems get worse and even more complex as clusters get larger, because now you have the problem of keeping configuration in sync across all of the nodes in that cluster. Maintenance, due to maintenance cycles, you may have a node that is temporarily down. Simultaneously, another operator might be pushing a configuration change for the cluster. Now what happens when that node that had been down comes back online? How do you guarantee that that node is receiving the good configuration best practices that were being deployed at the time that it was down? And also, over time, we notice a trend that clusters tend to get heterogeneous hardware. So that complicates the configuration situation as well.
So now that we have seen different war stories, we also generalize them in different patterns. Let's see how to win such wars, or preferably how to avoid such wars. And that's where SmartSense comes into picture. So SmartSense is essentially a solution for proactive support and personalized cluster recommendations, which exactly addresses the problem that we have seen in previous slides. The way it handles is basically it provides 3 different levels of support systems. First thing is it enables you to do faster case resolution by collecting data from your entire cluster with simple clicks. Second thing is it applies all the best industry practices to your cluster, to your version of Hadoop, for your specific cluster, specific hardware, so that you don't have to go through all those hundreds of parameters yourself. System does it for you. And it does proactively so that you can find issues even before they become real problems, and you can apply the recommendations appropriately. It essentially is a collection of tools that helps you collect data from cluster and execute multiple set of rules on the runtime environment of your cluster. We have multiple rules, and all these rules are very, very dynamic, which are developed in conjunction with the committers and developers. Also, we get a lot of feed from different sources, like our support engineers, like our solution engineers, like our professional services, who can see new things coming in the field, new patterns, new best practices, and feed that back into the rule system, where we can continuously improve our rules, add more rules, and start executing onto your cluster, even without having to change anything on your cluster. You automatically get new benefits just like that. Of course, it is a continuously evolving process. So let's talk about the SmartSense architecture, how it looks like. So this might be a typical cluster where you have multiple nodes, which may be managed by Apache Ambari. On each of these nodes, you would have SmartSense agents installed. So you can see that SmartSense agents are running on each of the nodes. All they do is they collect configurations, metrics, various reports, and logs from each of these nodes. Later, that information is sent to a SmartSense server, which aggregates all the data, anonymizes, encrypts that data, and finally sends that data through gateway server to a landing zone. So the gateway server helps you get data out of your data center securely, brings that into landing zone, where we execute our SmartSense analytics on top of that data, generate recommendations, which are then ready for you to review and also apply to your clusters. So let's see how SmartSense could have addressed those war stories. And we can go by all the stories and review them again.
Returning to the first story of instability in Hdfs, a name node that was frequently failing over in an HA deployment, the questions we have coming out of an incident like that are, what is the right heap size for my name node, my particular cluster? What should be the new generation size based on that heap size? The new generation is the portion of the JVM heap where newly allocated objects begin life. Which garbage collection algorithm should we use? Now that we know the algorithm, are there particular configuration options that need to be applied in addition to that? And finally, what if my cluster grows? What if I create a good configuration now, but cluster grows over time and I need to tune that? SmartSense's response to that is a SmartSense rule, Hdfs NN JVM opt. The implementation of this rule calculates the correct heap size based on current heap usage, total number of metadata objects in the file system, and also following a set of best practices that we've had for a long time about what works well for heap configuration and garbage collection configuration at the name node. It then recalculates the dependent JVM options based on the heap size. So for example, the new generation size is calculated as a function of total heap size. It validates that the existing JVM options are implemented correctly to follow these best practices, and if not, it provides recommendations to implement them. Since SmartSense is something that can be run continually, many times throughout the lifetime of a cluster, you can get notifications when you need to increase heap size or change garbage collection tuning. Digging into that calculation a little bit more, for the heap size recommendation, we estimate 200 bytes per Hdfs metadata object, such as files, directories, and blocks. We assume a 25% buffer so that there is some room for cluster growth over time. We have a recommendation to set the minimum Java heap size at process start and the maximum size to the same value, and that's something that's done to prevent an expensive reallocation halfway through the lifetime of the Java process. Based on usage patterns we've observed, we recommend the new generation size is 1/8 of that total heap size, but we put a hard cap on it at 8 gigabytes as well. And we recommend using the concurrent mark sweep garbage collection algorithm, and there are a set of configuration properties that go along with that. These are all best practices that we've been recommending for a long time for Hadoop clusters based on our experiences operating them. SmartSense is now taking those best practice recommendations and automating the process of checking that clusters have them deployed and providing recommendations when they don't.
The other story that we talked about, exceptionally high CPU usage for a cluster. So it was because of THP, if you recollect it. So if you want to figure out what to do in your particular cluster's case, you again have to answer multiple questions. The first thing is THP applicable for me? Is it applicable for my OS and my OS version? If it is applicable, is it disabled? Is it completely disabled? Is it disabled across all the nodes of my cluster? What would happen if I add more nodes to my cluster? How can I make sure that even new nodes have THP disabled? And finally, how can I make it this particular case person independent so that when different team members from my team or new team members of my team start applying different changes, they don't do some different standards? So of course, we have a rule that checks THP for your cluster. On each and every node, it goes and checks what is operating system, is THP applicable for you, and is it disabled? So it also provides operating system specific recommendations that you can easily take and apply across your cluster. And more importantly, since this happens continuously, as your decommissioned nodes becomes recommissioned, or if you add new nodes to your cluster, they also get validated, and they're also made sure that they're consistent across your clusters. So this is an example of these operating systems, Red Hat and CentOS, as well as Debian and Ubuntu, to set your THP to be disabled for specific versions of your operating systems, specifically 6.5 and below. So this graph actually shows what happened after THP was disabled. So you can see the first half of the graph is the cluster had THP enabled. The job was running. The system CPU was exceptionally high, the red part. Half of the graph shows, the later half of the graph shows when THP was disabled and the jobs were rerun, you can see that system CPU has been significantly gone down. At the same time, your network throughput has significantly gone up. So you can see that simple configuration change can have significant impact on overall throughput of your cluster.
Returning to the story of a cascading failure in Hdfs after an upgrade, the questions we have coming out of that incident are, should I finalize the upgrade? What is the right time to finalize the Hdfs upgrade? And how do I make sure it just doesn't fall through the cracks? It's a very simple thing to do. Perhaps because it's so simple, it's very easily forgotten as well. SmartSense handles this situation with a rule called Hdfs and then finalize upgrade. The implementation of this rule checks Hdfs health after the upgrade. It evaluates how long Hdfs has been running in an unfinalized state, and if that gets too long, it provides a reminder that it really should be finalized. I mentioned earlier the rolling upgrade window is designed to provide a window for validation of a new software version to make sure it's working correctly. We do recommend after an upgrade that you take that window to verify files and blocks are correct after the upgrade. The Hdfs FSCK tool is something that can be helpful for that. We also recommend running critical jobs at least once after the upgrade. In practice, what we observe is that this process takes 2 to 7 days after the upgrade. That will vary depending on workloads in the cluster. Some workloads will run out of space more quickly because they're ingesting data more quickly, and deletes are not keeping up because deletes do not physically delete blocks during the upgrade window. You can see on the left here, there is a visualization of the name node web UI showing a banner under the menu saying that the upgrade has not been finalized. That information is sourced from metrics, JMX metrics that are served over HTTP, and you can see that data in the raw form on the right where it says the upgrade is not finalized. The command to run is very simple, hdfs dfs admin -finalize upgrade, or you can automate it by just clicking through in the Umbari UI. Very simple, it's just important to remember to do it, and that's what SmartSense can provide here.
The fourth story that we talked about was overloaded cluster. And it was overloaded because their container configurations were not optimally configured. Now, this is one question that keeps coming back very frequently because it's very hard to answer this particular question because there are so many different variables involved in there. So obviously, when you start designing your container sizes, the question is that, what is the right container size for my cluster? even if I calculate container size for my cluster today, what happens if I add more services to the node? Specifically services like Storm and HBase, which have significant resource consumption. How would my container size change? Or how would my container size change when I add new nodes to my cluster which have different hardware profile? Because as you go and grow your cluster, eventually you're going to find better hardware with cheaper cost, which is going to have potentially more CPUs, more memory, more disk, and better performing disk. How do I make sure that my old hardware as well as my new hardware is fully utilized and my container sizes take care of all such variations? Or what if I add SSDs to my existing hardware? How would container size change? So of course, there are rules that we have in SmartSense that address container sizes for various technologies. So of course, you start with the Yarn. So we have rules for Yarn container sizes, then MapReduce container sizes, and Tez and Hive container sizes. The way these rules are executed is it looks at all the CPU resources available on all the resources available on your cluster, specifically on individual nodes like CPU, memory, number of disks, type of disks, and various services running. Based on that, it calculates technology-specific recommendations and tells you exactly what configurations you should set for your Yarn, Hive, Tez, MapReduce, these components. And of course, this happens continuously, so that when you add new workloads, when you add new services, when you add new nodes to your cluster, these calculations get triggered, and you are continuously prompted with new optimal configurations for your cluster. So drilling down, this is how container sizing is done. The first thing is you identify all the resources on your individual hosts, like CPU, memory, disks, number of disks, and type of disks. And for services that are running on each host, you keep aside some resources. So if you have Hdfs region server running, if you have Storm running, or anything else running, keep some resources aside for those particular services. Now, from remaining resources, you have to calculate what are the maximum number of containers that each of these resources can support. So you go by CPU containers, disk containers, memory containers. We have given some factors here that you can use to calculate how many containers each of these resources can really support. And finally, once you have these calculations for individual resources, as you know, you can be as fast as weakest link in your cluster. So finally, you take min of all these different containers, and that is going to be optimal container size for that particular node. And these validations happen for each and every node. And then based on this, you reconfigure your Yarn container sizes, and you can get much better performance.
Returning to our last Hdfs story, it was the accidental deletion of critical data sets. And coming out of that incident, a couple of questions that we have are, is Hdfs trash enabled? It's something that needs to be enabled in configuration. What is a safe trash interval, meaning the period of time that trash data is retained before it's really completely deleted? And how can we prevent accidental deletion of critical data? So SmartSense handles this with actually a set of two different rules. One is called Hdfs trash interval. This rule checks if trash is enabled and validates that the trash interval is within a reasonable limit. And a separate rule called Hdfs NN protect imp DIRs takes advantage of a new feature that's launching in Apache Hadoop 2.8.0. This new feature lets you specify in configuration a list of critical directories, and for any directory in that list, the delete operation is protected in that it does not allow the delete to proceed unless the directory is empty. So it's intentionally putting an additional barrier in the way of accidentally deleting large subtrees that amount to sacrificing a ton of data.
And this is one really good example where SmartSense kind of tools can really help you. As you can see that the second rule is coming in the new version of Hadoop. So when things are changing, when Hadoop versions are improving and new features are coming in, SmartSense automatically gathers this data from various sources so that you don't have to go through all those hundreds and thousands of JIRAs to figure out what is new for your cluster and what to apply. It does happen automatically for your systems.
Digging into those rules a little bit more, the first is looking at configuration property fs.trash.interval. This property both enables the feature and also defines the retention period. We have a recommended range of 1 to 7 days. And the rationale for that is, first, if you can imagine a scenario of deleting data at the end of the day, you want enough of a safety net so that people can return to work the next day and still have some time to react to the situation, still have that data in trash capable of being restored. If you follow the same line of reasoning to the weekend, you want enough protection in place that if a delete is issued late in the day on Friday, you still have an opportunity when you return to work Monday morning to react to the situation and restore that data from trash. So based on that, we recommend a range of 1 to 7 days with a midpoint of 3 days. The second rule looks at configuration property fs.protected.directories. Again, this is taking advantage of a feature in Apache Hadoop 2.8.0. So this is interesting as an example of a rule that is dynamic based on the version that you are actually running in your cluster. And it looks to make sure that the set of directories listed here is configured in that configuration property.
And the last story that we had was Hive query returning random results, which all happened because one of the node had different time zone. Now, how can we actually make sure that all my cluster is consistently configured? Time zone is just one factor. There are many such things. How about Java versions? How about users and user IDs and ulimits and various other things? How can we make sure that they're consistently configured across all my cluster? What happens when my nodes go down and maintenance cycle happens? When they come back and I recommission them, how do I make sure that they're consistently configured again? Same thing with adding new nodes. Because when you add new hardware, you might have changed your standards. You might come up with new Java version, new OS version, or variety of such things. How can I make sure that I have always consistent configurations across all my clusters so that I don't have to go through that painful analysis to figure out that my time zone actually caused my query results to go wrong? So of course, there's a rule in SmartSense which makes sure that your time zone across all the nodes are consistent. It also makes sure that not just time zone, but you have NTPD service running, which makes sure that your time is in sync with standard times. It also verifies that each of the NTPD servers are actually pointing to the right server so that the time across all the hosts is in sync. Because if it is not in sync, you can have issues like Hive query, or you may have serious issues on Hdfs clusters where region servers will start dying off. Now, these are just a couple of rules around consistency. There are many other rules: Java versions, user configurations, ulimits, and a variety of such things. It is practically impossible for somebody to keep running these rules or keep creating such new rules and making sure that they're always consistent across all your cluster. So what we talked about is just 6 such stories and 6 such configurations. There are many, many more things. SmartSense has 250 plus more such rules that help you understand and analyze these kind of issues and address them before really they become a problem. There are rules around operations, how to make your operations easy, how to make your cluster more stable and improve your uptime. There are rules around improving security of your cluster across all the components. There are rules around improving performance of your cluster, performance of individual jobs, individual components, as well as throughput of your overall cluster. Now, it is practically impossible or unfair to understand or expect from Hadoop admins to know all such things and continuously keep applying and validating clusters. It's practically impossible for somebody to do that. And that's where systems like SmartSense can really, really help customers to do these things for them so that customers and Hadoop operation teams can focus on tasks which makes bigger impact on their business and their departments. All other mundane tasks can be automated by systems, and you are given appropriate recommendations when needed to make your Hadoop cluster much more better, faster, stable, and secure.
We've seen now a couple of examples of how SmartSense can perform analysis on configuration of a cluster and provide recommendations based on that. But fully understanding Hadoop operations involves more than just configurations. It also involves looking at which jobs have a significant impact on my cluster, especially if you are running a multi-tenant deployment with lots of users with a variety of workloads. It also is good to examine what type of workloads are running on my cluster. Who are the top users of my platform? Again, looking at the multi-tenancy use case. How do I improve the performance of key jobs? Very often, because of the 80-20 rule, there are a small set of jobs that, if optimized well, free up a lot of capacity for executing other jobs, and it's good to look at those. How do I charge back to multiple different tenants running in a Hadoop cluster based on their activity? And finally, what is a good time for maintenance? Ideally, maintenance would be performed at the time of least impact when there's the least activity running on the cluster so that it causes harm to the least number of users if something were to go wrong.
So of course, there are questions like this and many more questions like this that Hadoop admins would want to understand and get answers to so that they can become a really good Hadoop operators and make their cluster one of the best. And to get this data, to get these answers, there is data spread across multiple components, multiple sources. It's very, very difficult to get that data, track that data, and come to meaningful conclusions. So that's why we have added something called activity analysis in SmartSense. So using activity analysis, basically there is a daemon in SmartSense which goes and watches all the activities happening in the Hadoop cluster. Activities are typical activities like running MapReduce job, Tej job, Yarn application, and so on. All these jobs are watched, analyzed, their data is put in a database, which is then later on available for queries, where you can see meaningful details and insights into your cluster and cluster operations. And you can take better decisions on how to operate your cluster more efficiently and effectively. You can get reports like, which are my top 10 longest running jobs, so that you can figure out how to make them run faster. Or which are my jobs that are asking for large resources. And by large resources, we mean many, many containers and huge containers, because they can have serious impact on your overall cluster throughput. Importantly, which are the jobs that are wasting resources? And by that, we mean that jobs that are asking for large containers, large resources, but practically not using it, just holding on to them, just blocking, and not letting others also use it. This was a war story that we talked about. Or get different insights into what types of jobs are running on my cluster, so that I can figure out how to optimally configure my cluster for those kind of workloads. Or which are the users which are actually writing a lot of data to Hdfs and reading a lot of data from Hdfs. I can see that how can actually help those users to understand better techniques so that they can do their task with much more efficiencies. As you may know that having a lot of very, very, very small files on Hdfs is not something that Namenode likes. So understanding that what is the file distribution of your Hdfs cluster, how many small files you have, understanding who creates those small files, understanding which jobs create those small files will give you very, very detailed insights into your data sets, and then it can help you improve your cluster performance by taking appropriate actions, because you know exactly where the problem is. Or you can also see what is the typical pattern of job execution, on what particular day, at what particular time jobs get submitted, so that you can address other questions like, what is the right time for my cluster maintenance, so that I have least impact on my tenants. Or you can also use this information to figure out, to add new jobs, what is the perfect time to add new jobs, so as to figure out and make sure that these jobs get enough resources so that they are not waiting in the queue. So in summary, so we're running out of time. I think just a couple more minutes and we will be done with this. So to summarize, as you have seen, that there are many, many things in operating Hadoop cluster. Many components, many configurations, hardware profiles, different types of workloads. All these things really matter. And the best practices that we have, they keep evolving, because technology is changing so fast, the best practices also keep evolving. What you configured for today and what is running well for today may not be the right thing for tomorrow, because your cluster topology might have changed. You might have added more nodes of different types. You might have added more data. You might have added more workload. So you need to adapt to changing nature of your cluster to make sure that your cluster is appropriately tuned for those changing workloads. So doing this manually, of course, is going to be really, really brutal work. And systems like SmartSense can definitely help you improve your cluster by fixing these common mistakes and preventing issues before they become problems, so that you, as Hadoop operators and admins and users, can focus on more meaningful and more productive tasks and make your Hadoop journey more rewarding and fulfilling. So with that, let's keep your Hadoop cluster at its best. Thank you.
Thank you. Yes.
So SmartSense has two components. So the question is, what is the footprint of SmartSense on a cluster? SmartSense has two key components, agents and server. Agent is a passive agent, which is not continuously running daemon. It is woken up only for capture. So there is really no footprint on individual data nodes. Only for that capture duration, which is typically few minutes, 3 to 5 minutes, the agents wake up and they collect data. All they need is very little memory, little CPU, and disk space based on how many logs you have in your cluster. The server, on the other hand, is a continuously running process. All it really needs is 8 gigs of RAM, and that's it. Any other questions? Yep.
Is there any plans to move that analysis back into Embari locally?
So,
Because like I have clients, obviously they're not going to share that data outside of the cluster, right? So me sending any metrics from the cluster to someone else is just a no-go.
So the very good question, and this keeps coming back very frequently. We do have plans to feed the intelligence of SmartSense back into Ambari, but the problem with that is the Ambari adoption it depends on the release cycles of Ambari. Having these rules somewhere outside gives us ability to create rules and deploy them literally multiple times a day. That we cannot do when it is part of Ambari, because you're limited by Ambari release cycles, and when you actually upgrade your Ambari cluster to the newer versions. So that's why we intentionally want to keep it outside so that you can get new rules, because literally, as I said, as we resolve support cases, we come up with new patterns, new best practices, new rule is developed and immediately deployed. That agility you cannot get immediately if it is part of Ambari, because you have to practically upgrade it. To address your concern about security, we have many customers who had similar concerns, banking customers, financial customers. What we have done in the product is we have many rules around security. We have inbuilt rules that go and anonymize all critical data. All passwords are automatically dropped. All important data like IP addresses, domain names, they're automatically anonymized. And then remaining data is again encrypted. So what you get out of your cluster is already anonymized and encrypted data, where you're actually not sharing any sensitive information. On top of that, if you feel that there is something sensitive for your cluster, you can add your own custom anonymization rules to drop such data sets. So you have even much better and bigger control of what to share and what not to share. So with that, most of our customers are able to understand that and then go forward with SmartSense.
So the global cluster configuration isn't always the configuration that individual jobs or individual tools use. A lot of tools want you to take your global configuration and then tweak it a little bit for their particular workloads. Does SmartSense detect patterns and possibilities for improvement at the job level to say, for this job or that job, you could increase this parameter, decrease this parameter?
Great question. So generally, SmartSense looks at improving your overall throughput of your cluster. So it gives a global recommendation. But as you know that many of these configurations can be overwritten by job level. So the first level of recommendation that you get are at cluster level to make sure that you have better throughput of your cluster. The activity analysis I talked about, it also has one component which goes and analyzes individual jobs and gives you very specific recommendations that what can you do for this job to improve its performance. Not just configuration, but it can identify different issues like, are there long tails? Do you have data skew that is making your job run for a very long time? Do you have capacity scheduling issues that are actually not letting your job get enough containers to execute? So it can have multiple different rules very specific to that job, and you get job specific recommendations too. That right now is only for MapReduce and things. Eventually we'll add for other jobs like Spark and other workloads. But most of the current workloads are typically MapReduce, Thais, and Hive queries and Yarn applications. So you'll get those things. It is coming out in the July release.
Great, thank you.
Okay.
So your backend server is a hosted solution, right?
Yes.
It's a SaaS service.
Yeah.
So do you have plan to offer a service that people can install on-prem and run it?
So eventually, yes, there are many customers who ask for that. But as I said, mainly for the agility reason, agility purpose, we want to make sure that we got to get to a maturity level where we have all the possible analytics inbuilt and deployed there. Because right now we have extremely fast-paced deployment. Literally every day, every week, we're adding new rules. That we cannot do on hosted environments. So that's why we're intentionally, to get better benefits for customers without them changing anything, we're hosting it right now. Eventually, we may think about having on-prem solutions. But right now, there is no immediate plan for that. Okay? Yeah, sure.
Just a short yes or no. Does it have any Kerberos support?
Yes, it does support. It does support Kerberized clusters. It does support all the platforms that we support as part of HDP, all the operating systems, HA-enabled clusters, HA-enabled on Hdfs, HA-enabled on Resource Manager, as well as fully Kerberized cluster. It does support that. SmartSense itself doesn't need Kerberized cluster because it's a different service, unlike Hdfs or Resource Manager. But it does support Kerberized clusters.
And even speaking specifically to Hdfs, there's a separate set of rules that get triggered when Kerberos is enabled in a cluster, so we can check for more, for tighter security controls in that cluster. Yep.
Right. If there are no more questions, thank you. Thanks a lot for
Thanks,
joining
everyone.
us.
Hey.